Our sun shines in solitary silence, but that is not the fate of every star. Picture a cosmic dance of 6 suns, all gravitationally bound in an intricate celestial ballet. These are sextuple star systems, and they defy everything we think we know about stellar families. You are about to embark on a journey through 50 of the most mind-bending discoveries astronomers have made about these cosmic oddities. You will learn how they create stellar vampires, forge rogue planets, and even challenge Einstein's theory of gravity. How can a family of 6 stars survive without tearing itself apart? What kind of worlds could possibly form in such chaos? By the end, you will see our quiet corner of the galaxy in a completely new light. What does true cosmic chaos look like to you? High in the winter sky, the twin stars of Gemini have watched over humanity for millennia. But one of those twins, the brilliant point of light we call Castor, has been keeping an extraordinary secret. For centuries, astronomers gazing through their telescopes saw what they believed was a classic binary star, 2 suns forever orbiting one another. The truth, uncovered only with the most advanced instruments, is far more spectacular. Castor is not 2 stars but 6. It is the first sextuple star system ever identified by humanity, a cosmic matryoshka doll of stellar relationships. At its heart are not 6 individual stars but 3 pairs of binary stars. Each pair is a tightly bound couple whirling around one another in a frantic embrace. Then those 3 pairs themselves are gravitationally linked, all dancing around a common center of gravity in an orbital configuration of breathtaking complexity. This makes Castor not merely a collection of stars but a hierarchical system, a family with a very specific pecking order. Discovering this arrangement was like realizing a single person you spotted on a distant hill was actually 6 identical twins moving in perfect, synchronized formation. The stability of this celestial ballet is what makes Castor so foundational. Its very existence proved that multi-star systems could be far more complex and far more organized than anyone had dreamed, setting the stage for our hunt for other stellar sextets and rewriting the rules of how star families can exist. While Castor reveals a stable family dance, some stellar sextets are born in cosmic pressure cookers. Consider the system known as AR Cassiopeiae. Here, 6 stars are bound together in an embrace so intimate it defies all expectations of personal space. The entire complex sextuple system could almost fit inside the orbit of Mercury around our own sun. Picture our solar system as a vast, empty arena. Now compress 6 raging, gravitationally intertwined suns into a space smaller than that single inner orbit. This is not a slow, stately waltz. It is a frantic, chaotic scramble in a gravitational arena with no room to breathe. The consequences of such extreme proximity are violent and constant. Tidal forces of unimaginable strength relentlessly squeeze and stretch these stars, warping their spherical forms into egg-shaped monstrosities. This gravitational friction heats their outer layers to blistering temperatures, fundamentally altering how they age and evolve. The stars are so close that their outer atmospheres can literally touch, creating bridges of superheated plasma. This leads to a phenomenon astronomers call mass transfer, where one star acts as a vampire, siphoning material directly from its companion. This stolen fuel can rejuvenate the vampire star, making it appear younger and hotter than it truly is, while dooming its donor to a premature and unusual stellar death. Such intimate interactions completely rewrite the standard timeline of stellar evolution, creating cosmic Frankenstein's monsters that should not exist according to our textbooks. How can a system this chaotic and violent even form, let alone survive for millions of years without instantly collapsing into a cataclysmic fireball? The violence of systems like AR Cassiopeiae reveals just how chaotic a sextuple star's youth can be, but some systems preserve that ancient chaos in frozen form. Far from the crowded stellar scramble, the system known as HD 98800 presents a different kind of mystery. At first glance, it appears to be a quadruple system, two pairs of stars orbiting one another. Yet these four are themselves part of a wider gravitational dance with another distant binary pair, making it a full sextuple. But the true enigma lies around one of the inner pairs, where a vast, misshapen disk of dust and rock whirls in a turbulent storm. This is not a calm, orderly protoplanetary disk like the one that gave birth to our solar system. It is a shattered wreck, a ring of debris filled with strange gaps and bright clumps. Astronomers studying its structure have found compelling evidence that this chaotic disk is a cosmic crime scene. The clues point to a startling conclusion that a seventh star once tried to form here. In the frantic gravitational tug of war between the existing 6 stars, this budding stellar embryo was starved, shredded, and ultimately torn apart before it could ever ignite. What we see now is the leftover building material, the gravel and dust that never coalesced into a sun, forever trapped in the conflicting gravitational pulls of its stellar siblings. This failed star is the ghost in the machine, a permanent testament to the system's violent birth. Its remnant disk is now a place where planets could never peacefully form, a celestial junkyard that tells the story of a family that was almost one member larger. The ghost of a failed star in HD 98800 shows the destructive potential of 6 suns, but other sextuplets push that chaos into the future. New Scorpii is a system living on borrowed time. Its structure is a masterpiece of celestial architecture, but one with a fatal flaw. At its core are 2 pairs of stars, each a tightly bound binary whirling in a frantic dance. These 2 pairs then orbit each other at a wider separation, and this entire quartet is itself locked in a grand, slow dance with a 5th star, which is actually another close binary completing the set of 6. This makes New Scorpii a system of dizzying complexity, with orbits nested within orbits like a set of cosmic gears. For now, these gears are turning, but the machinery is fundamentally unstable. The gravitational pulls between all 6 bodies are not perfectly balanced. Over millions of years, these tiny, persistent tugs will accumulate, subtly altering the orbits in a process called dynamical instability. It is a system forever on the verge of collapsing under the weight of its own relationships. This makes New Scorpii a living laboratory for gravitational dynamics. Astronomers can run sophisticated computer simulations to forecast its fate, and the predictions are dramatic. The most likely outcome is a violent restructuring. One star, likely from one of the inner binaries, could be slingshotted out into the void of interstellar space, becoming a runaway star forever exiled from its family. Alternatively, the unstable dance could decay into a catastrophic merger, where 2 stars spiral inward and collide in a titanic explosion of light and energy. Either event would permanently rewire the system, collapsing the sextuple into a quintuple or a different, more stable configuration. We are witnessing a temporary and ultimately doomed celestial balancing act. How long can such a fragile family hold itself together before gravity demands a final, brutal reckoning? The fragility of New Scorpii hints at the violent futures of these systems, but some sextuples may already hide that violence in their past. Consider the brilliant beacon of Beta Lyrae, a star system that has puzzled astronomers for over 2 centuries. To the naked eye, it is a single point of light, but we now know it is a complex sextuple arrangement. Its most famous component is an eclipsing binary, 2 stars so perfectly aligned from our viewpoint that they regularly pass in front of each other, causing the system's light to dramatically dip and rise in a predictable rhythm. Yet that rhythm holds a strange anomaly. The timing of these eclipses is not perfectly constant. It wavers, speeding up and slowing down by tiny, precise amounts. This minuscule hiccup in the celestial clockwork revealed the gravitational tug of a mysterious 3rd body orbiting the central pair. Calculations of its mass, however, presented a profound mystery. This unseen object possesses the gravitational heft of several suns, yet it emits no light, no heat, no radiation that our telescopes can detect. It is a dark, massive ghost haunting the inner binary. The leading theories are as breathtaking as they are unsettling. This could be a stellar mass black hole, the corpse of a massive star that lived fast, died young, and collapsed in on itself, now silently lurking within its stellar family. Alternatively, it might be a neutron star, a city-sized ball of impossibly dense matter left behind by a supernova. Both are stellar corpses, remnants of a cataclysm that this system somehow survived. How does a family of 6 stars endure the violent death of one of its own? A supernova explosion powerful enough to blast a system apart. The fact that this dark component remains gravitationally bound suggests the sextuple's dance is resilient enough to withstand even a stellar apocalypse, forever hiding a monument to its own ancient tragedy in the silent tug of gravity. The silent black holes of Beta Lyrae are not the only dark secrets these systems conceal. Entire worlds born in the outer calm of a sextuple system are often sentenced to a life of eternal exile. Within the swirling disks of gas and dust that can surround these stellar families, the seeds of planets begin to form, far from the gravitational storm of the inner stars, in regions where the pull of the central dance weakens, rocky cores and gaseous giants can slowly coalesce. For a time, it seems a new world has found a stable home, but the stability is an illusion. The complex gravitational field of 6 stars is a perpetual earthquake. As the inner binaries whirl around each other, their combined gravitational pull does not emanate as a smooth, constant force. Instead, it acts like a series of unpredictable kicks, a cosmic paddleball machine of immense power. When a young, newly formed planet drifts into just the right or just the wrong position in its orbit, it can receive a sudden and immense gravitational slingshot from one of these inner stars. This kick transfers a tremendous amount of energy to the planet, boosting its velocity far beyond the escape velocity of the entire system. In an instant, a world is violently ejected, cast out from its stellar family to drift alone in the cold, dark expanse between the stars. These are rogue planets, and sextuple systems are prolific factories for them. Computer simulations reveal a brutal truth. For every planet that manages to hold onto a stable orbit in such a system, dozens more are likely hurled into the abyss. This means the galaxy could be teeming with these solitary wanderers, dark worlds with no sun to warm them, forever orphaned by the chaotic families that gave them birth. What would it be like to stand on the surface of such a world beneath a sky of permanent, starry night, your solar system nothing but a receding memory? A star can hide its deepest secrets in the rhythm of its vanishing light. In the constellation Cepheus, the massive supergiant VV Cephei performs a celestial disappearing act so slow it defies human perception. This is an eclipsing binary, a pair of stars where one regularly passes in front of the other from our viewpoint. But this is no quick flicker. The primary star is a behemoth, one of the largest known stars in our galaxy. Its companion, a smaller but fiercely hot blue star, takes a staggering 20 years to complete a single orbit. The eclipse itself, when the blue star finally slips behind the vast, cool expanse of the supergiant, lasts not for minutes or hours, but for an entire year and a half. For nearly 500 days, the system dims as the brilliant blue light is swallowed whole. Yet it is the strange precision of this epic dimming that revealed the system's true nature. Astronomers meticulously tracking the timing of these 20-year cycles noticed a subtle, persistent wobble in the schedule. The eclipses were not arriving exactly on time. They were minutely early, then fashionably late in a repeating pattern that spanned decades. This was not an error in measurement, it was a gravitational fingerprint. The clockwork of the central binary was being gently sped up and slowed down by the invisible tugs of 4 other stars orbiting far beyond the main pair. Each slight deviation in the eclipse timetable was a clue, a mathematical whisper of an unseen companion's gravity pulling on the dance. By decoding these rhythmic hiccups, astronomers pieced together the full picture, a sextuple system where the motion of two colossal stars acts as a sensitive gauge for the four fainter members we could not directly see. It is a profound demonstration that even the simplest observation, the dimming of a star, can unravel a symphony of gravitational relationships across unimaginable distances. The explosive death of a star should be the ultimate family destroyer. A supernova unleashes more energy in a few seconds than our sun will produce in its entire lifetime, and this cataclysm is often accompanied by a powerful natal kick. As a star's core collapses into a neutron star or black hole, asymmetries in the explosion can launch the newborn corpse across space at speeds exceeding 1,000,000 miles per hour, a velocity designed to break any gravitational bond. Yet within the intricate dance of a known sextuple system, astronomers have found a ghost that defied this violent birth. The gravitational tugs within the system reveal the presence of a massive, dark object, a neutron star or black hole, that remains stubbornly bound to its stellar siblings. This presents a monumental puzzle. How could this remnant have survived the supernova kick that should have flung it into the galactic void? The answer may lie in the unique dynamics of its stellar family. In a sextuple system, a dying star is not just bound to one partner. It is enmeshed in a complex web of gravitational relationships with 5 others. The combined pull from multiple stars, all acting from different directions, could have created a gravitational net strong enough to catch the remnant, arresting its escape velocity and tethering it back into the dance. Alternatively, the supernova itself might have been unusually symmetric, a gentle sigh rather than a violent shout, resulting in a minimal kick that the system's gravity could easily withstand. Either scenario forces a rewrite of stellar death models, suggesting that the survival of a stellar corpse is not a matter of chance, but a consequence of the family it keeps. The quiet persistence of this dark remnant proves that even a stellar apocalypse is not always enough to break the bonds of a truly determined cosmic family. The survival of a stellar corpse proves the gravitational bonds in these systems are incredibly resilient. Yet this same resilience might actively prevent the formation of certain types of planets. Across our galaxy, one of the most common exoplanets discovered is the hot Jupiter, a gas giant orbiting perilously close to its parent star. But within the known sextuple systems, these blistering worlds are conspicuously absent. It is a profound cosmic silence. The chaotic gravitational environment that can catch a runaway black hole seems to be utterly hostile to the existence of a close-orbiting giant planet. How could a force powerful enough to hold a system together also create a planetary dead zone? The leading theory points to orbital instability from the very beginning. For a hot Jupiter to form, it needs a calm, stable disk of gas close to the star. In a sextuple system, the gravitational tides from multiple stars constantly stir the protoplanetary disk, creating violent waves and gaps that disrupt the slow, gentle process of planet formation. The gas simply cannot coalesce into a giant world when it is being perpetually shaken. Even if a hot Jupiter somehow managed to form farther out and migrate inward, as some theories suggest they do, its journey would be a suicide mission. The complex gravitational kicks from the other stars would constantly perturb its orbit. Instead of settling into a stable, close-in path, the planet would be sent on a wildly erratic trajectory. It would either be flung out of the system entirely to become another rogue planet, or its path would decay, sending it spiraling directly into its host star in a final, fiery embrace. The absence of these planets is a direct signature of the immense forces at play, a celestial environment so turbulent that it forbids the very existence of a class of worlds we find everywhere else. A star's death is meant to be a singular, final event, but in the gravitational web of a sextuple system, even this cosmic finale can be hijacked. Deep within one such family, a white dwarf star, the dense, Earth-sized core of a deceased sun, is locked in a macabre dance with a nearby companion. Like a cosmic parasite, the white dwarf's immense gravity relentlessly strips hydrogen-rich gas from its partner, pulling the stolen material into a swirling, searing hot disk around itself. This stream of stellar plasma continuously rains down onto the white dwarf's surface, steadily increasing its mass, and with mass comes a terrifying threshold, the Chandrasekhar limit. If a white dwarf accumulates enough matter to exceed this critical weight, the resulting pressure and heat in its core becomes so extreme that it triggers a runaway thermonuclear explosion. In a solitary system, this would be a Type 1, a supernova, a single cataclysmic detonation that would utterly annihilate the white dwarf, yet here that final death is denied. The intricate gravitational ballet of the other 5 stars subtly regulates the flow of stolen material. The accretion is not a steady stream, but a series of pulses and surges. This means the white dwarf's mass teeters just at the brink of destruction, never quite accumulating enough for a full supernova all at once. Instead, it crosses the threshold in bursts. Every few decades, the accumulated layer of hydrogen on its surface reaches a critical density and ignites in a colossal but partial thermonuclear blast. This is a recurrent nova, an explosion violent enough to outshine its entire stellar family for a few weeks, blasting the recently stolen material back out into space. The white dwarf survives the blast, wounded but intact, only to immediately begin the cycle of theft and accumulation all over again. It is a stellar zombie, perpetually dying in a series of violent eruptions, yet always clawing its way back from total annihilation, resurrected by the very gravitational forces that keep it prisoner. This endless cycle forces us to ask a disturbing question: is this star truly dead, or is it trapped in the universe's most agonizing and spectacular purgatory? The endless death throes of a stellar zombie are a spectacle of light, but some of these systems resonate with something far more fundamental: the silent music of spacetime itself. Deep within the crowded cores of certain sextuple families, the tightest binary pairs are not just stars, they are gravitational wave factories. These are often pairs of incredibly dense objects, 2 white dwarfs or neutron stars locked in a final, frantic embrace. As they whirl around each other at immense speeds, they do not orbit in perfect silence. According to Einstein's theory of general relativity, their tremendous acceleration creates ripples in the very fabric of space-time, gravitational waves that radiate outwards at the speed of light. This emission of energy comes at a direct cost to their orbit. With every wave they send out into the universe, the 2 objects lose a tiny amount of orbital energy, causing them to spiral imperceptibly closer together. Over millions of years, this slow, relentless decay will inevitably lead to their collision and merger. Future observatories like the space-based Laser Interferometer Space Antenna, or LISA, are being designed specifically to listen for the faint hum of such events. But in a sextuple system, the soundtrack is not a single, pure tone. The gravitational pull from the other 4 stars in the wider dance constantly tugs on this inner binary. This external influence minutely speeds up and slows down the inward spiral, modulating the frequency and pattern of the gravitational waves they produce. Instead of hearing a lone violin, Lisa would detect a complex cosmic chorus, a signal rich with the gravitational fingerprints of every single star in the system. Decoding this chorus would not just tell us about the dying binary, it would reveal the precise masses and orbits of its 4 distant siblings, offering a complete map of the entire sextuple family written not in light but in the vibrations of spacetime. The silent hum of gravitational waves is a testament to order, but the planets that survive in these systems often bear the scars of chaos. astronomers discovered a world orbiting one star in a sextuple family, a rare survivor in the gravitational storm. Yet this planet is fundamentally askew. Its orbital plane is severely tilted, angled dramatically away from the equators of its host stars and from the orbital plane of the wider stellar dance. This is not a planet that formed in a calm, flat disk. It is a world that has been violently thrown off course. Imagine a spinning top on a perfectly level table, then striking it sharply with a hammer. The top would wobble wildly, its axis of spin knocked into a new, tilted orientation. This planet experienced a gravitational hammer blow. The most likely culprit was a close encounter with another star in the sextuple system. As the 6 stars whirl through their complex dance, their paths are not perfectly circular or eternally stable. Millions of years ago, this planet's host star may have swung perilously close to one of its stellar siblings. The resulting gravitational tug of war did not eject the planet. Instead, it delivered a powerful off-center pull, a cosmic side swipe that torqued the planet's entire orbit, tipping it over into its current misaligned state. This single, tilted world is therefore a permanent record of a past dynamic instability. It tells us that the serene dance we observe today was not always so orderly, that the system has a history of close calls and gravitational violence. The planet's strange path is a fossil, preserving the memory of a stellar near collision that forever altered its journey around its sun. Our tilted planet is a monument to past gravitational violence, but the chaos does not end at the edge of its orbit. Far beyond the inner turmoil, in the frigid outer darkness of a sextuple system, lies a vast reservoir of ancient ice. This is the Oort cloud of the system, a spherical shell of trillions of pristine, icy bodies left over from the system's violent birth. In our own solitary solar system, our Oort cloud is a relatively peaceful place, its comets only occasionally disturbed by a passing star. But here, with 6 suns constantly tugging from the center, this outer domain is a perpetual gravitational shooting gallery. The combined pull of the 6 stars creates a chaotic environment where the orbits of these icy bodies are never truly stable. A distant, slow-moving comet minding its own business can receive a series of tiny gravitational nudges from the complex inner dance. Over millions of years, these small kicks can add up, altering its path just enough to send it falling inward on a death dive toward the central stars. But for some, the outcome is even more extreme. A perfectly timed gravitational slingshot from one of the stellar members can impart a tremendous burst of speed. This kick is so powerful it does not send the comet inward, but rather gives it enough energy to achieve escape velocity from the entire system. In a flash, the icy body is ripped from its gravitational family and hurled into the deep void of interstellar space. It becomes a permanent wanderer, a lone iceberg on an endless journey between the stars. We have already seen 2 of these visitors from other star systems, the bizarrely shaped Oumuamua and the more familiar-looking comet Borisov. Their origins have been a profound mystery. While they could come from many types of systems, sextuple stars are prime suspects as prolific interstellar comet factories. The relentless gravitational turbulence they generate makes them exceptionally efficient at manufacturing and launching these icy messengers. Every time we spot one of these strange objects drifting through our neighborhood, we could be witnessing the final, long-range product of a chaotic family of 6 suns, a piece of cosmic debris ejected from a gravitational storm that began light years away and eons ago. These stellar tantrums are born from a state of perpetual hyperactivity deep within the star itself. The same gravitational tides that warp stellar forms also act as a powerful brake and accelerator, dramatically altering a star's spin. As stars in these tight binaries are pulled and squeezed, their rotation speeds up, much like a spinning ice skater pulling in their arms. This rapid rotation churns the star's interior, amplifying its magnetic dynamo to levels far beyond our sun's. The result is a chromosphere, the star's outer atmosphere, that is supercharged and violently unstable. it becomes a cosmic pressure cooker of magnetic energy. When tangled magnetic field lines suddenly snap and reconnect, they release cataclysmic bursts of radiation, stellar flares of unimaginable ferocity. A single one of these eruptions can unleash more energy than 1,000,000 of the largest solar flares ever recorded from our own sun. Simultaneously, vast regions of intense magnetic activity create sunspots that dwarf our entire planet, dark blemishes covering a significant fraction of the stellar surface. This relentless activity makes the entire system an unpredictable and hostile environment. A planet orbiting one of these hyperactive stars would be subjected to a constant barrage of radiation storms and charged particles, effectively sterilizing its surface and shredding any potential atmosphere. The very space around these stars crackles with a level of magnetic violence that redefines what it means to be an active star, proving that in a family of 6, even a sun's temper can be pushed to its absolute breaking point. This stellar vampirism is not a gentle sip but a violent feast. Deep within one of these 6-star families, a celestial predator is at work. A massive, greedy star circles a smaller, cooler companion in a tight, frantic orbit. Their closeness is the key to the crime. The immense gravity of the larger star reaches out, and because the two are so near, it can get a firm grip on the outer atmosphere of its smaller sibling. It does not just pull, it rips. A constant stream of superheated hydrogen gas is torn from the victim star, siphoned across the void between them. This stolen material does not fall directly onto the predator. Instead, it forms a swirling, searingly hot disk of plasma, whirling around the massive star like water circling a drain. This is an accretion disk, a cosmic crime scene glowing with the evidence of the theft. The violence of this process heats the disk to millions of degrees, causing it to radiate intensely in high-energy X-rays, while the stolen stardust also glows with an infrared heat signature. From our distant vantage point, this system appears as a brilliant, multi-wavelength beacon of stellar cannibalism. The vampire star, gorging on this fresh fuel, becomes unnaturally bright and hot, its life extended by the consumption of its partner. The donor star, meanwhile, is left scarred and diminished, its outer layers peeled away to reveal a hotter, denser core prematurely. It is a stellar relationship that completely inverts the natural order, where one star's longevity is purchased with the slow destruction of another. How long can this parasitic dance continue before the victim star is completely consumed, or the system is thrown into chaos by the shifting weights of its members? This stability seems to defy the very chaos that defines them. While many sextuple systems are cosmic powder kegs, astronomers have uncovered a remarkable few that have endured for billions of years, outliving entire galactic eras. Their secret lies not in luck but in a precise celestial architecture known as orbital resonance. In these rare, ancient systems, the orbits of the stellar pairs are not just random paths. They are locked in a precise gravitational rhythm, like interlocking gears in a perfect cosmic clock. The orbital periods of the stars form neat integer ratios with one another. For every 3 orbits one binary pair completes, another pair might complete exactly 2 or 5. This synchronization is the system's safety lock. These resonant orbits create a repeating gravitational pattern. Instead of pulling chaotically and unpredictably, the star's tugs reinforce a stable, repeating cycle. It is a gravitational conversation where every participant knows its lines and speaks them at exactly the right time, preventing the small, cumulative tugs from escalating into a destructive frenzy. These configurations are always hierarchical, with tight inner binaries and progressively wider outer orbits, creating a clear gravitational pecking order that minimizes direct interference. The existence of these geriatric sextuples forces a profound shift in our understanding. Complexity does not automatically spell a short, violent demise. With the right gravitational choreography, a family of 6 suns can achieve a harmony so perfect it can last for eons. a serene island of order within a universe often dominated by stellar chaos. What other ancient, complex dances are waiting to be found, their rhythms still perfectly in time after all these years? These stars carry the permanent scars of their cosmic feasts in their very light. When astronomers point their spectroscopes at the members of a sextuple system, they are not just measuring brightness, they are reading a detailed chemical recipe of the star's atmosphere. In several of these complex families, that recipe reveals bizarre and unexpected ingredients. Some stars show a puzzling overabundance of lithium, an element that is normally destroyed in the hot nuclear furnaces of a star's core. Others display unusually high concentrations of heavy elements like carbon, nitrogen, or even rare earth metals, a composition that defies their age and mass. These are not random anomalies, they are the chemical fingerprints of stellar cannibalism. The explanation lies in the violent mass transfer between binary partners. When a vampire star siphons material from its companion, it is not just stealing hydrogen fuel, it is consuming the entire layered chemistry of its victim. If the donor star had already begun fusing elements in its core, those newly forged heavier elements can be ripped from its interior and dumped onto the surface of the predator. This process can dredge up lithium from layers where it should have been burned, or coat a star in carbon that was cooked deep inside its partner. The result is a star with a chemical identity crisis, its outer layers telling the story of two different stellar lives fused into one. This altered composition becomes a permanent record, a celestial autopsy report that allows astronomers to reconstruct ancient acts of cosmic violence long after the turbulent accretion disks have faded away. How many other stars wear the ghostly chemical signatures of companions they have consumed? These runaway stars are celestial fugitives blazing across the galaxy at incredible speeds. Astronomers have now become cosmic detectives, tracing the fiery paths of these high-velocity outcasts backward through time. The trails consistently lead them back to the same kind of place, dense, turbulent stellar nurseries, the very cradles where sextuple star systems are born. The connection is too strong to be a coincidence. The leading theory paints a dramatic picture of gravitational betrayal. Within a young, unstable sextuple system, the orbital dance can turn deadly. During a close encounter, two of the stellar members can swing perilously near one another. In that moment, their immense gravitational fields act like a slingshot, transferring a tremendous burst of kinetic energy to one of the stars. This kick is so powerful it completely overcomes the system's gravitational pull. The star is not gently nudged out, it is fired away like a celestial cannonball, achieving an escape velocity that can exceed 1,000,000 miles per hour. It leaves its entire family behind in an instant, doomed to forever wander the interstellar void alone. We can actually measure these speeds. One famous runaway star, known as Mu Columbi, is racing away from its birthplace in the Orion Nebula at a staggering speed. If you could stand on a planet orbiting this star, you would see its former home, the nebula where it was born, recede into the distance at an unimaginable rate, a fading memory of the family that violently expelled it. These runaway stars are not just curiosities, they are living proof of the chaotic gravitational environments that define their origins, permanent exiles carrying the signature of their explosive birth. The brilliant point of light we call Polaris, the North Star, has guided travelers for centuries. It appears as a solitary beacon of constancy, a perfect singular sun. Yet this is a cosmic illusion. Polaris is not one star but three, and this is the rule, not the exception, for many of the most famous stars in our sky. The light of Castor, the first sextuple we met, arrives at our eyes as a single, steady glimmer. For generations, astronomers using the finest telescopes of their era saw only a binary star, completely missing the four other members of the family. The sheer distance to these stellar systems compresses their complex dances into a single, unresolved point. The problem is not the brightness, but the angular separation. Even with a massive telescope, the turbulent soup of our own atmosphere blurs the fine details, smearing multiple stars into what appears to be one. The true revolution in understanding came not from building bigger lenses, but from developing cleverer ways to see through the atmospheric haze. Speckle interferometry, a technique developed in the late 20th century, works by taking thousands of incredibly short exposure images in rapid succession. Each image freezes the atmospheric distortion for a fraction of a second, capturing fleeting moments of clarity. Advanced computers then combine these thousands of snapshots, statistically analyzing the speckled patterns to reconstruct a crystal-clear picture that reveals stars huddled impossibly close together. At the same time, spectroscopy unmasked companions we could never see directly. By splitting a star's light into a rainbow spectrum, astronomers can detect the subtle, rhythmic wobbles in its color. As a star moves toward us, its light is squeezed, shifting slightly toward the blue end of the spectrum. As it moves away, the light stretches toward red. In a sextuple system, this creates not a single, clean wobble, but a complex symphony of shifting colors, the gravitational fingerprint of multiple invisible partners tugging the star back and forth. It was through this precise spectral analysis that the dark, massive object in Beta Lyrae was first suspected. These techniques have peeled back the sky's greatest deception, revealing that a stunning number of the stars we consider solitary are in fact crowded metropolises. The familiar constellations above are not a simple collection of lone suns, but a vast, hidden network of complex families, their true nature written in a language of light and wobble we have only just learned to read. These stellar families are cosmic laboratories for the most fundamental laws of physics. The complex gravitational dance within a sextuple system pushes Einstein's theory of general relativity to its absolute limits, offering tests of precision impossible to replicate anywhere else. One of the most powerful probes is a phenomenon called periastron precession. In a simple binary system, two stars orbit each other in a repeating elliptical path. But according to general relativity, in an intense gravitational field, that ellipse does not quite close perfectly. The point of closest approach between the two stars, the periastron, slowly shifts forward with each orbit. It is as if the ellipse itself is slowly rotating, tracing a spirograph pattern in the sky over long periods. In a typical binary, this effect is minuscule. But within the tight, fast-whirling binaries at the heart of a sextuple system, the gravitational fields are so extreme that this precession is dramatically amplified. We can measure it not over centuries, but sometimes within just a few years. Any tiny discrepancy between the observed precession and the prediction from Einstein's equations would signal a crack in our foundational understanding of gravity itself. So far, general relativity has passed every test, but astronomers watch these systems intently, knowing they are one of the most likely places to find a deviation that could unlock a new physics. Another critical test comes from the very timing of starlight. When the light from one of these distant stars finally travels across the immense void to reach our telescopes, it has battled its way out of a deep and complex gravitational well. According to Einstein, gravity warps spacetime, and light climbing out of that warp loses energy, causing its waves to stretch slightly. This is gravitational redshift. In a sextuple system, as stars whip around each other at ferocious speeds, and their light emerges from the combined gravity of multiple suns, this redshift becomes a measurable signal. Furthermore, when one star in an eclipsing binary passes behind another, its light must travel through the curved spacetime of its companion to reach us. This creates a tiny but detectable delay in the eclipse's timing. These minute delays, these subtle stretches in starlight, are all precisely predicted by general relativity. The fact that they match observation so perfectly in these chaotic six-star environments is a stunning confirmation that Einstein's vision of gravity holds true even in the most extreme gravitational arenas the universe can construct. The universe has its own atomic clocks, and they are spinning in the heart of these stellar families. A pulsar is a neutron star that has survived a supernova, and its rotation is so stable it rivals our most precise human-made timekeepers. These cosmic lighthouses sweep beams of radiation across space with a rhythmic tick, tick, tick that is predictable down to the microsecond. But when a pulsar is one member of a sextuple system, its perfect rhythm is not quite perfect. The regular pulse begins to stutter. It arrives a fraction of a second early, then a hair late in a complex repeating pattern. These are not errors. They are messages. Each tiny deviation is a direct measurement of the gravitational pull from one of the pulsar's 5 sibling stars. As the stars move through their intricate dance, their shifting positions change the strength and direction of their tugs on the pulsar. This subtly alters the path its radio signals must take to reach us, creating a minute but measurable delay. By decoding this intricate pattern of pulse delays over years, astronomers can perform a feat of celestial cartography that borders on magic. They can calculate the exact mass of every single star in the system, even the dim, faint ones hidden in the glare of their brighter siblings. They can trace the precise shape and orientation of every orbit, mapping the entire gravitational architecture of the 6-star family without ever directly seeing most of its members. It is like listening to the faint echoes in a dark, complex cavern and being able to draw a perfect 3-dimensional map of every wall and chamber based solely on the sound. This pulsar timing array transforms the entire system into a natural gravitational laboratory, offering a window into the hidden mass and structure of one of the universe's most complex families. The violent birth of a sextuple system does not just create stars, it actively engineers the nursery itself. The same gravitational collapse that forms 6 suns sends powerful ripples through the surrounding molecular cloud. The most massive stars in the newborn family ignite with ferocious intensity, blazing with ultraviolet radiation and blasting out supersonic winds of charged particles. This is not a gentle process, it is a celestial bulldozer. Imagine a bubble of unimaginably hot gas expanding into a cold, dark cloud of hydrogen. This powerful shockwave slams into the surrounding gas, compressing it into dense, ragged sheets and filaments. Within these newly pressurized pockets, the delicate balance of the cloud is shattered. Gravity, once held in check by internal gas pressure, suddenly finds itself with the upper hand. These compressed regions cross a critical threshold and begin to collapse under their own weight, igniting the nuclear furnaces of a second generation of stars. We see this echoed in famous stellar nurseries like the Orion Nebula, where the brilliant trapezium cluster's radiation is actively sculpting new stars out of the surrounding cloud. A sextuple system is an even more concentrated and potent version of this phenomenon. It becomes the epicenter of its own miniature starburst, a gravitational domino effect where one act of cosmic creation forcibly triggers the next. The system is not merely a resident of the nursery, it is its architect, using its own explosive birth to manufacture stellar siblings and fill the void with new light. The strange chemistry of these stellar families is written not just in starlight, but in the ghostly glow of their dust. Orbiting observatories like the Spitzer Space Telescope and its mighty successor, the James Webb Space Telescope, have turned their infrared eyes toward the dusty disks and shrouds within sextuple systems. They have found a spectral mystery, a set of broad, smeared-out emission features in the infrared data that defy all our earthly catalogs. These are not the sharp, clean fingerprints of familiar molecules like water or carbon dioxide. They are messy, unidentified bands of light, a cosmic signature with no known author. The leading suspect is a form of matter forged only in the stellar infernos of such complex systems. The intense and varied radiation from 6 different stars, each blasting the surrounding dust with its own unique blend of ultraviolet and X-ray light, acts as a colossal laboratory. This radiation bath can process simple carbon grains and ices into bizarre, complex macromolecules. They could be vast, tarry sheets of carbon, exotic chains of hydrogen and carbon atoms, or even tiny, cage-like structures, all radiating heat in a way we have never seen in any laboratory on Earth. These unexplained emissions are a direct result of the system's chaotic environment, a chemical factory where the rules of formation are rewritten by the combined light of 6 suns. What new states of matter, what alien forms of dust are being concocted in these cosmic cauldrons? These chemical anomalies are a prelude to an even more dramatic stellar transformation. Scattered throughout ancient sextuple systems, astronomers find brilliant blue stars shining with a deceptive youth. They are called blue stragglers, and their existence is a direct challenge to our understanding of stellar life cycles. In a cluster of stars, everything is born at roughly the same time. The most massive stars burn hot, blue, and fast, dying young. The lower mass stars are cooler, redder, and live for billions of years. This creates a clear pattern on a graph of stellar color and brightness, a well-defined sequence where stars of a certain mass have a certain lifespan. Blue stragglers shatter this pattern. They are stars that should have aged into red giants or dimmed long ago, yet they blaze with the hot, blue intensity of a star in its prime. They are stragglers lagging behind their siblings in the race toward stellar death. The crowded, chaotic environment of a sextuple system provides the perfect breeding ground for these stellar imposters. The leading theory is one of violent creation. In the tight gravitational dance, 2 lower mass stars, perhaps a binary pair that has drifted too close to another star, can be forced into a cataclysmic merger. When 2 stars collide, their outer layers violently mix, churning fresh, unburned hydrogen from their outer regions into the hot core. This injection of new fuel completely rejuvenates the resulting single star. It becomes more massive, hotter, and bluer, effectively resetting its evolutionary clock. It is a stellar phoenix born from a collision, now masquerading as a star far younger than it truly is. This process is a direct consequence of the system's density. In a calm, solitary system like our own, such stellar collisions are unthinkably rare. But in the gravitational pressure cooker of a sextuple family, where stars are perpetually nudged onto erratic paths, mergers become a predictable, almost inevitable part of the life cycle. The blue straggler stands as a permanent monument to a forgotten stellar union, a single star living a life that was meant for 2. A stellar explosion is the universe's ultimate act of creation. When the most massive star in a sextuple family reaches the end of its life, it does not fade quietly. Its core collapses in a cataclysm known as a supernova, a blast of such ferocious energy that it momentarily outshines its 5 remaining siblings. In that brief, unimaginable inferno, the star becomes a cosmic alchemist. The intense heat and pressure forge elements far heavier than the hydrogen and helium it was born with. Deep within the fireball, atomic nuclei are slammed together with such force that they create the very metals that define our world, the iron in our blood, the gold in our jewelry, even the radioactive uranium that heats the Earth's core. This is nucleosynthesis at its most violent and productive, but in a solitary system, this newly forged treasure would be blasted out into the lonely void, lost to the interstellar medium. The magic of a sextuple system is its gravitational bond. The supernova, despite its power, is often not strong enough to completely unbind the family. The 5 other stars act as a gravitational anchor, holding a significant portion of the expanding debris cloud within their collective pull. This means the supernova's precious, heavy element-rich ejector does not simply vanish. Instead, it is captured. This metallic cloud then begins to rain down upon the surviving stars and any surrounding protoplanetary disks, seeding them with the raw ingredients for rocky planets. A star that was born from pure hydrogen and helium can suddenly find its environment, and even its own atmosphere enriched with gold, platinum, and uranium. Any new planets that form around these enriched stars will be born with a far richer composition, increasing the chances of forming metallic cores, rocky crusts, and complex chemistry. The violent death of one star becomes the creative genesis for future worlds, a celestial inheritance written in the language of atomic nuclei. The very materials that make our own Earth possible may have been forged in a similar, ancient supernova within a complex stellar family, a gift from a long-dead star to its siblings. A star's vanishing act can become the most precise clock in the cosmos. Deep within a sextuple system, a pair of stars locked in an eclipsing binary provides this perfect celestial timepiece. As they orbit, one star passes directly in front of the other from our viewpoint, causing the system's combined light to dim in a perfectly predictable rhythm. This rhythm is so regular you could set your watch by it, with eclipses repeating over days, weeks, or even years with unerring accuracy. But this perfect clock does not always tick on time. Astronomers meticulously tracking these events across decades sometimes notice a tiny hiccup. An eclipse arrives a few seconds early. The next one might be a fraction of a minute late. These deviations are far too small to be random error. They are a gravitational fingerprint. The invisible hand of the system's other four stars is at work. As those unseen siblings move through their own complex orbits around the central binary, their combined gravity tugs on the eclipsing pair. When they pull the binary slightly toward us, the light has a shorter distance to travel, and the eclipse appears to arrive a tiny bit early. When they pull the binary away, the light takes longer to reach us, and the eclipse is fashionably late. By meticulously mapping these minuscule timing variations, a process known as eclipse timing variations, astronomers can perform a feat of celestial deduction. They can calculate the precise masses of the unseen stars, even though they have never directly observed their light. They can trace the exact shapes and sizes of their orbits, mapping the entire hidden architecture of the system. It is like listening to the steady tick of a pocket watch, and from the almost imperceptible wobbles in its rhythm, being able to draw a perfect picture of every invisible hand that is shaking the table it rests upon. This single, rhythmic binary becomes a master timeline for the entire sextuple family, its slight stutters betraying the silent, massive presence of its dark companions. A star's chaotic birth leaves its mark long before its nuclear heart ignites. Deep within stellar nurseries, astronomers have spotted infant sextuple systems still cocooned in their wombs of gas and dust. These are T-Tauri stars, stellar newborns blazing with the fierce energy of gravitational collapse, not yet stable enough for core fusion. Each of the 6 infant suns is often encircled by its own swirling protoplanetary disk, a potential birthplace for future worlds. But the scene is one of profound gravitational interference. The disks are not the calm, flat platters we see in artists' conceptions of our own solar system's origin. They are warped and twisted, their inner edges abruptly truncated by the immense gravitational pull of a nearby stellar sibling. Vast gaps carved through the dust, not from the gentle shepherding of a newborn planet, but from the relentless, chaotic tugs of 5 other suns. The potential for planet formation is being sculpted and dramatically limited from the very first moments. A particle of dust trying to coalesce into a pebble faces a constant barrage of gravitational kicks. Just as it begins to stick together, a passing star's gravity sends it veering off course, shattering delicate structures and preventing the slow, gentle accumulation that builds planets. The very architecture of these young systems seems designed to forbid the creation of stable, orderly solar systems, creating instead a turbulent nursery where the seeds of worlds are scattered before they can ever take root. How could any world hope to form in such a gravitational storm, where the very cradle of creation is perpetually being shaken? The combined gravity of 6 suns does more than just bind them together. It warps the very space around them into a colossal lens. This is not a lens of glass, but of pure space-time, a curvature so profound it can alter the path of light itself. Picture a single, brilliant quasar billions of light years behind a sextuple system. Its light travels for eons across the universe, only to encounter this massive gravitational knot in its final approach. The space-time curvature around the six stars acts like a vast, lumpy lens, bending the incoming rays of light. Instead of arriving at our telescopes in a single, straight line, the quasar's light is forced to take multiple different paths around the stellar family. Each path is a different journey, some longer and more circuitous than others. The result is not one image of the quasar, but several. We would see multiple, faint, and often strangely stretched copies of the same distant object arrayed around the sextuple system, a cosmic mirage known as an Einstein cross or an Einstein ring. But this lens is far from perfect, because the mass is not concentrated in one point but is spread across six stars in a complex dance. The resulting images would be warped and distorted in a unique way. Their shapes would tell a precise story about how the mass is distributed throughout the entire system. Furthermore, since each path the light takes has a different length, the images would not be in sync. An outburst of brightness in the quasar would appear in one image days, weeks, or even months before it appeared in another. By meticulously tracking these time delays between the multiple mirages, astronomers could perform an extraordinary feat of cosmic measurement. They could essentially weigh the entire sextuple system, calculating the precise mass of every star, both bright and dark, and even map the contours of the gravitational well they collectively create. This natural telescope, forged by gravity alone, offers a way to probe the hidden architecture of these families, using the distorted light of the distant universe to illuminate the secrets hidden in our own galactic neighborhood. Surrounding these stellar families, space itself can glow with a heat born of pure violence. When astronomers point X-ray telescopes toward massive sextuple systems, they often find them encased in vast, shimmering bubbles of invisible light. These are not gentle halos, but colossal structures of gas heated to millions of degrees. Their creation is a relentless, high-energy battle. Each of the six massive stars in these systems blasts its surroundings with a powerful stellar wind, a supersonic gale of charged particles flowing from its surface at millions of miles per hour. In the solitary calm of our solar system, the solar wind flows outward unimpeded. But here, with six stars in close quarters, these winds do not flow freely. They collide. Where the hurricane force winds from two stars slam into each other, they create a standing shock wave, a wall of pure force in space. The gas caught in this collision is compressed and heated instantaneously, like air in front of a supersonic jet, but on a cosmic scale. The temperature soars so high that the gas does not just glow with visible light, it radiates intensely in high-energy X-rays. With six stars all contributing their gales, the result is a complex, churning cauldron of these shock fronts, a tangled web of superheated plasma that envelops the entire system in a brilliant, if invisible, X-ray aura. This ongoing collision of winds acts as a powerful feedback mechanism, regulating the very environment of the stellar family. The hot, high-pressure bubble it creates pushes back against the inflowing gas from the stars themselves, limiting how much material can be siphoned between them and potentially stifling the growth of the most massive members. It is a perpetual, high-stakes territorial war, fought with gales of star stuff, whose only visible sign is a ghostly glow of X-rays that reveals the ferocious energy of a space perpetually in turmoil. A single star's path across the cosmos is meant to be a straight line, a perfect arc dictated by the galaxy's rotation. Yet in a nearby sextuple system, one star's journey tells a different story entirely. Its motion is not straight, but a slow, meandering wobble, a gentle sway against the backdrop of more distant stars. This is the astrometric wobble, a telltale sign of an invisible companion's gravity. The star is not traveling alone. It is perpetually tugged to the side by the mass of its unseen partner, causing it to trace a minuscule loop in the sky every few centuries. Detecting this wobble is one of astronomy's most painstaking endeavors. It requires measuring the star's position with microscopic precision, year after year, decade after decade, waiting for the pattern to reveal itself over a timescale that can span 1,000 years. This is not work for a single lifetime, but for generations of astronomers adding their meticulous data to a collective celestial map. The wobble we see today might have begun its current cycle before the invention of the telescope. Each new measurement is another point on a graph that will not be completed for centuries, a testament to human patience in the face of cosmic time. What other long-period companions are silently tracing their slow dances around these stellar families, their presence known only by the gentle, persistent sway they impose on the stars we can see? Far from the pristine hydrogen clouds of the early universe, some stellar families are born with a silver spoon in their mouth. Astronomers analyzing the light from sextuple systems deep within the galactic bulge have uncovered a chemical oddity. These stars are metal-rich. In astronomy, the term metal refers to any element heavier than helium, from the carbon in your bones to the iron in the blood of a distant world. These elements are not forged in the Big Bang. They are cooked in the nuclear furnaces of stars and scattered into space by supernova explosions. A high metallicity is a sign of cosmic inheritance, proof that the gas cloud from which these stars formed had already been seeded and enriched by countless stellar generations that lived and died before them. The sheer abundance of these heavy elements in these particular sextuples is surprisingly high, far exceeding what we see in many other parts of the galaxy. This single measurement acts as a powerful time capsule, locking in the chemical history of the galactic bulge. It tells us this densely packed central region of our galaxy underwent a period of intense, rapid star formation and death long before these 6 star systems even began to collapse. Their very existence and their rich composition forces a recalibration of our models for how quickly the galactic core built up its heavy elements. How many stellar lives were sacrificed to create the specific chemical recipe that would one day give rise to such a complex and metal-laced family of stars? Deep within the tangled orbits of a sextuple family, some stars pulse with a rhythmic light that mimics a living heartbeat. These are heartbeat stars, close binary pairs whose light curves show a gentle, recurring pulse of brightening and dimming. This is not caused by one star eclipsing the other. Instead, it happens when the 2 stars, following elongated oval-shaped orbits, swing perilously close at their point of nearest approach. Their immense gravitational fields stretch each other, pulling the stellar spheres into egg-shaped forms. This tidal distortion causes their surface area and brightness to briefly increase, creating a subtle yet detectable heartbeat in the data before the stars swing apart and relax back into spheres. In a solitary binary, this heartbeat is a clean, predictable pulse, but place that same passionate couple inside a sextuple system, and the rhythm becomes a complex, syncopated drumbeat. The gravitational pull from the other 4 stars constantly tugs on the binary's orbit, minutely altering its shape and timing. They squeeze the oval path, making it more or less elongated. They speed up or slow down the orbital clock. Each of these tiny perturbations imprints itself directly onto the heartbeat signal. The pulse may arrive slightly early, or its peak might be a little higher or lower than expected. What appears as a simple rhythm is actually a convoluted symphony of gravitational influence. By decoding the precise pattern of these hiccups and modulations, astronomers can listen to the gravity of the entire system. The heartbeat becomes a diagnostic tool, its irregularities mapping the precise masses and orbits of the other, seemingly unrelated stars. It is a conversation in light, where the most intimate dance of 2 stars is made to betray the silent presence of their entire celestial family. A star's journey across the galaxy should be a stately, unbroken arc, but astronomers tracking the motion of certain sextuple systems have noticed their paths are not perfectly straight. Over decades of observation, the entire system's glide against the backdrop of more distant stars shows a subtle but definite wiggle, a gentle kink in its course. This deviation is known as a proper motion anomaly, and it represents the ghostly signature of the system's internal dance. Every time one of the 6 stars swings around its partner, or a binary pair completes an orbit, the system's center of mass shifts slightly. It is like watching a group of friends walking while tightly holding hands. If one person suddenly spins around another, the entire group's forward motion will jostle and swerve. These tiny, cumulative swerves, when measured over years, trace out a pattern. That pattern is a direct record of the gravitational pushes and pulls happening inside the system, a kind of celestial fingerprint left on the fabric of space itself. By analyzing the precise shape and size of this wobbling path, astronomers can perform a remarkable feat of cosmic accounting. They can add up the gravitational influence of every single object in the system, both seen and unseen, and calculate the system's total mass. This method is incredibly powerful because it does not require us to see every star. Even faint, dark components like white dwarfs or stellar mass black holes, which might otherwise remain hidden, betray their presence through their collective gravitational pull on the system's trajectory. The entire family of 6 is weighed together by the slight imperfections in its voyage, a silent confession of its total mass written in the star's slow drift across the sky. The very cradles of worlds are warped by this gravitational storm. High above the deserts of Chile, the Atacama Large Millimeter Array, a forest of radio antennas, has peered into the hearts of these systems, capturing images of the dusty disks where planets are born. What they reveal is not the calm, orderly platter we see in models of our own solar system's infancy. Instead, these protoplanetary disks are misshapen and agitated. They are scarred with bright, lumpy clumps of dust and gas, their smooth surfaces broken by grand, sweeping spiral arms that look more like a miniature galaxy than a planetary nursery. These are not features born from within. They are the direct fingerprints of the other 5 stars, their gravitational tides perpetually kneading the disk like a cosmic hand working a lump of dough. A star might be trying to form a planet in one quiet corner of its personal disk, but the gravity of a sibling star passing nearby sends a powerful ripple through the material. This ripple compresses the gas, triggering the growth of a dense, bright clump that could be the seed of a future gas giant, or it might simply be a transient feature destined to be scattered by the next gravitational pulse. Those majestic spiral arms are themselves waves of density, stirred up by the rhythmic tugs of the wider stellar dance. This is a birthplace in perpetual turmoil, where the very process of planet formation is orchestrated not by one star but by 6. What kind of world could possibly coalesce from such a dynamically agitated, unpredictable environment? Lithium acts as a cosmic clock for sun-like stars. This fragile element, one of the first 3 forged in the Big Bang, is easily destroyed in a star's hot interior. Normally, a star's outer layers protect a small, measurable amount of lithium, and this reserve slowly depletes over billions of years, providing a reliable gauge of stellar age. Yet within the chaotic embrace of a sextuple system, this clock appears broken. Astronomers find sun-like stars here with atmospheres almost completely scrubbed clean of lithium, as if they were ancient geriatrics, but their other characteristics suggest they are surprisingly youthful. This bizarre depletion points to a violent internal remodeling. The relentless gravitational tides from multiple companion stars act like a colossal spoon, violently stirring the star's interior. This forced mixing dredges up deep, lithium-poor material from the core to the surface, while dragging the surface lithium down into the scorching depths where it is instantly incinerated. The star's own structure is being churned from the inside out, erasing its chemical memory and presenting a false age to the cosmos. What other secrets of stellar evolution are being rewritten by this perpetual gravitational stirring? A brilliant yellow supergiant star burns at the heart of a known sextuple system, and its very presence is a ticking clock. This stage of stellar life is one of the most fleeting and unstable in the universe. A star only shines as a yellow supergiant for a few 100,000 years before it either collapses into a supernova or swells into a cooler red supergiant. To find one here, entangled in the complex gravitational web of 5 other stars, is like finding a single fingerprint on a cosmic murder weapon. It tells astronomers exactly what they are dealing with. The mass of this star, and by extension the likely masses of its siblings, must be within a very specific range to have reached this precise, short-lived phase. Its brilliance acts as a calibrated beacon, allowing scientists to pin down the entire system's age with remarkable precision. This single star is therefore a crucial piece of a much larger astronomical puzzle known as the yellow supergiant problem. Our best models of stellar evolution predict that the universe should be teeming with these golden giants, yet our telescopes see far fewer than expected. Finding one in such a well-defined system where its mass and age can be so tightly constrained provides a critical reality check for those models. Is our understanding of how stars evolve fundamentally flawed, or are these brilliant phases simply even shorter and more violent than we thought? The sextuple system's captive supergiant offers a rare, controlled laboratory to find the answer, its fleeting light helping to solve a mystery that spans the entire cosmos. The spectacular complexity of a 6-star family points to a single, elegant process of creation. The leading theory for their birth is known as hierarchical fragmentation, a cosmic cascade of division. It begins with a single, massive cloud of cold gas and dust, a dark nebula drifting in the void. This cloud is not uniform, it is riddled with tiny pockets of slightly higher density. One of these pockets begins to win the gravitational tug of war, collapsing inward under its own weight. As it collapses, it spins faster, just like a figure skater pulling in their arms. This rapid rotation causes the central, collapsing core to flatten into a disk, but the process does not stop there. The disk itself is unstable, a fragile structure under immense gravitational stress. It cannot hold itself together, the disk fragments breaking apart into 2, 3, or even 4 distinct clumps of gas. Each of these clumps continues its own independent collapse, becoming a protostar. But the story repeats itself. Each of these new protostars is also spinning, and each can form its own small disk. These secondary disks then fragment again, creating even more stellar seeds. It is a process of cosmic subdivision, a single parent cloud giving birth to multiple children, which then give birth to their own stellar offspring. This is hierarchical fragmentation in action, a natural factory for binary and triple star systems. A sextuple system is simply this process pushed to its extreme, the result of a particularly large and fertile cloud undergoing multiple rounds of successful fragmentation. The very structure we see today, with tight binary pairs orbiting other tight binaries, is a frozen record of this step-by-step breakup. The existence of these stellar sextets is not a bizarre accident. It is the ultimate confirmation of a fundamental stellar birthing mechanism, a universe that prefers to build its stars in families of ever-increasing complexity. The gravitational fingerprints within these stellar families sometimes point to a presence that is neither planet nor true star. Meticulous analysis of the rhythmic color shifts in a star's light, the telltale wobble of the radial velocity method, has revealed massive, unseen companions silently orbiting within the sextuple dance. These objects possess the gravitational heft of dozens of Jupiters, yet they emit only a faint, deep red glow of residual heat. They are brown dwarfs, the failed stars of the cosmos. A brown dwarf is a celestial paradox, a ball of gas that gathered enough mass to begin collapsing like a star, but not enough to trigger the sustained nuclear fusion of hydrogen in its core. It is an object caught in a permanent state of almost a cosmic stillbirth that never truly ignited. Its faint light comes only from the slow, lingering heat of its violent gravitational birth, and it will spend eons fading into a cold, dark cinder. Finding such an object within a sextuple system adds a profound new layer of gravitational complexity. It acts as a missing link in the system's architecture, a bridge between the realm of planets and the domain of true stars. Its substantial mass exerts a quiet but persistent pull on its brighter siblings, subtly influencing the long-term stability of their intricate orbits. How many of these dim, fading embers are hiding within the crowded families we have already found, their silent gravity weaving an invisible thread through the already tangled web of 6 suns? While gas giants are flung into the void, a different kind of world might endure in these chaotic systems, a rocky super-Earth. Imagine a planet several times more massive than our own, forged from rock and metal far from the gravitational storm. Its orbit might be stable enough to avoid ejection, but it is far from peaceful. The planet is perpetually needed by the conflicting gravitational tugs of 6 different suns. This is not a gentle pull, but a deep, rhythmic flexing that warps the entire world, generating immense friction deep within its core. The result is a level of tidal heating beyond anything in our solar system. On Jupiter's moon Io, the gravitational pull of just one giant planet creates hundreds of active volcanoes, now amplified by the combined chaotic tides of multiple stars. The interior of this super-Earth would be a molten hell, its crust a thin, fractured shell floating on a global ocean of magma. Volcanoes would erupt not in isolated spots, but across the entire planet, constantly repaving the surface in rivers of fire. The atmosphere would be a toxic cocktail of volcanic gases, perpetually replenished and scorched by the intense heat. Such a world is the antithesis of life, a geological nightmare of perpetual upheaval. Yet its very existence would be a testament to the paradoxical nature of these systems, creating a stable orbit for a planet while simultaneously forging it into a vision of planetary inferno. What other forms of extreme worlds does the universe concoct when gravity itself becomes a relentless creative fire? A star's light can be made to confess its deepest secrets, but only if you know how to listen. When astronomers split that light into a rainbow spectrum, they find it etched with dark lines, the unique chemical fingerprints of the elements burning in the star's atmosphere. In a simple binary star, these spectral lines perform a predictable rhythm, shifting back and forth from blue to red as the 2 stars orbit their common center of gravity. But in a sextuple system, this rhythm shatters into pure chaos. The lines do not just shift, they writhe. They blur, split apart, and change shape in a complex, ever-changing pattern that looks less like a measurement and more like a frantic dance. This spectral scrambling is the direct result of the stars' overlapping motions, a Doppler shift cacophony. You are not seeing the light from one star being tugged by one partner. You are witnessing the combined light of 6 different suns, each moving at a different speed and in a different direction relative to us. One star in a tight binary is whipping toward us, blue shifting its lines, while its partner flies away, red shifting its own. Meanwhile, that entire binary pair is itself swinging around another pair, adding another layer of velocity change. The light from all these stars blends together in our telescopes, and their individual, conflicting Doppler shifts smear the sharp spectral lines into a messy, wobbling, and shape-shifting tangle. Decoding this dance is a monumental task of astronomical forensics. It requires sophisticated computer models to simulate every possible orbital configuration, tweaking the masses and orbits of 6 hypothetical stars until their predicted combined Doppler effect perfectly matches the bizarre, writhing lines we observe. When the model finally clicks, it doesn't just confirm the presence of hidden stars, it reveals the precise choreography of the entire family. That chaotic dance in the spectrum becomes a precise map, written in light, of one of the universe's most complex gravitational ballets. The final, dramatic act for some binary stars is a cosmic cannibalism that ends in a spectacular rebirth. Picture a star much like our Sun, but in its old age swelling into a monstrous red giant. Its outer layers expand until they no longer merely brush against its binary companion, but completely engulf it. For a brief, violent period, the smaller star orbits inside the atmosphere of the giant, like a planet circling within its own sun. This is the common envelope phase, a stellar struggle of immense proportions. The engulfed star does not go quietly. Plunging through the thick, diffuse gases of the giant, it experiences immense friction. This friction saps its orbital energy, causing it to spiral inexorably inward toward the giant's core. But this same friction also transfers a tremendous amount of energy outward, acting like a colossal engine. The entire bloated envelope of the red giant is violently ejected, blasted away into space to form a beautiful, shimmering planetary nebula. What remains is the naked, white-hot core of the original giant, now a white dwarf, locked in a desperately tight, fast orbit with the companion that orchestrated its unveiling. This is a post-common envelope binary, a stellar phoenix risen from its own ashes. Finding such a pair within a larger sextuple system is like discovering a fossilized record of this intimate stellar cataclysm. The wider gravitational dance of the other four stars was a silent witness to this drama, its presence potentially influencing the timing and outcome of the entire event. The tight orbit of the surviving binary is a permanent scar, the direct result of that frantic spiral through a stellar atmosphere, a dance of death that ended with the creation of a new celestial object and the beautiful, ephemeral ghost of a nebula. A Cepheid variable star is the universe's most reliable mile marker. These pulsating giants rhythmically brighten and dim over days or weeks, and the very pace of their heartbeat is directly tied to their true brilliance. By measuring the period of their pulse, astronomers can calculate their intrinsic luminosity, and by comparing that to how dim they appear from Earth, they can determine their distance with stunning precision. It is this relationship that first revealed the vast scale of our universe and proved other galaxies existed beyond the Milky Way. Yet within the gravitational storm of a sextuple system, this dependable cosmic ruler begins to warp. The rhythmic pulsations of a Cepheid, driven by a delicate balance of pressure and gravity within the star itself, are vulnerable to external interference. The relentless gravitational tugs from its 5 stellar companions act like a constant, invisible hand, squeezing and relaxing the star at the wrong moments. This external forcing subtly alters the star's natural rhythm, making its pulses arrive a little faster or slower than they should for a star of its mass and age. The period-luminosity relationship, the very foundation of our distance ladder, is thrown into disarray. A Cepheid in such a system might pulsate with the rapid rhythm of a young, less luminous star, while actually possessing the vast power of an older, brighter giant. If we were to use this distorted rhythm to calculate its distance, we would get a dangerously wrong answer. We might place a galaxy much closer or farther than it truly is, skewing our three-dimensional map of the cosmos. How many of our fundamental cosmic measurements, the very distances we use to trace the expansion of the universe, have been subtly corrupted by these chaotic stellar families? Untangling the gravitational influence on each Cepheid is like calibrating a watch while it is being violently shaken, a painstaking process essential to ensuring we are not building our entire view of the cosmos on a foundation of beautiful, pulsating lies. The chaotic winds and magnetic storms of these stellar families forge more than just light. Deep within the churning collisions of their supersonic gales, a far more elusive and energetic phenomenon is born. The violent shock fronts where stellar winds slam together at millions of miles per hour do more than just heat gas to X-ray temperatures. They act as nature's most powerful particle accelerators, far surpassing anything we could ever build on Earth. Within these colossal, natural laboratories, stray protons and electrons become caught in the maelstrom. The tangled, immensely powerful magnetic fields surrounding the stars trap these particles, forcing them to ricochet back and forth across the shock wave. With each crossing, the magnetic field transfers a little more energy, a tiny kick of speed, much like a ping-pong ball being batted faster and faster between two relentless paddles. Over time, this process accelerates the particles to velocities approaching the speed of light, transforming them into ultra-high-energy cosmic rays. A single proton accelerated here can carry the kinetic energy of a professionally thrown baseball, all compressed into a subatomic speck. These stellar families become brilliant, localized beacons of such radiation, contributing significantly to the galaxy's background fog of high-energy particles. While most cosmic rays are blocked by our atmosphere, these specific high-energy streams from systems like this are a reminder that the empty space between stars is not truly empty, but filled with a silent, invisible rain of atomic shrapnel, much of it launched from the gravitational fury of families with 6 suns. Even the most perfectly resonant orbits cannot escape the slow, cosmic drag of time. This is the work of dynamical friction, a subtle but relentless force that acts like an invisible brake on the entire system. Imagine a single star moving through a sparse sea of background material, perhaps the remnants of its birth cloud or a diffuse cluster of stars. As it travels, its gravity tugs on every particle it passes, creating a slight wake of denser material trailing behind it. This gravitational wake, in turn, pulls back on the star, ever so slightly slowing its motion. This is dynamical friction, a gentle tug that robs a moving object of its momentum. In a sextuple system, this effect is magnified by complexity. The wider binary pairs, those stars orbiting at a great distance from the system's center, are the most vulnerable. As they sweep through their long, slow orbits, they are not moving through empty space. They are plowing through the combined gravitational fields of their 4 sibling stars and any leftover gas or dark matter halo that might still cling to the family. Each passage extracts a tiny tax of orbital energy, causing the wider pairs to spiral imperceptibly inward, century after century, millennium after millennium. This gradual inspiral is a slow-motion rewriting of the system's architecture. A pair that once took 1,000 years to complete an orbit might, over millions of years, see that period shrink to 900 years, then 800. Its orbit becomes tighter, more circular, and more deeply enmeshed in the gravitational storm of the inner stars. This decay can fundamentally alter the system's hierarchy. A stable, wide orbit pair might be drawn so close to another binary that their gravitational conversation turns from a polite whisper to a disruptive shout, destabilizing the delicate dance that has held the family together for eons. The system you observe today is not the system it was, nor the system it will become, all thanks to the silent, accumulating drain of dynamical friction. Carbon is the fundamental ingredient of life, written in the very stars that are now dying. Within the geriatric sextuple systems that have endured for billions of years, some of the oldest members are reaching their spectacular finales as asymptotic giant branch stars. These swollen, brilliant giants are in a state of profound transition, no longer fusing hydrogen in their cores. Instead, they burn helium in a searing shell around an inert core of carbon and oxygen, while a separate outer shell continues to burn hydrogen. This double shell structure makes them cosmic pressure cookers of immense power. It is deep within the helium-burning shell that the universe forges one of its most essential elements through a reaction known as the triple alpha process. Here, under temperatures exceeding 100 million degrees, 3 helium nuclei are forced to collide and fuse in a precise, sequential dance, creating a single, stable nucleus of carbon. This is stellar alchemy at its most crucial, the primary source of all carbon in the cosmos. But in the chaotic embrace of a sextuple system, this delicate process is not left to its own devices. The mass loss from an AGB star is already immense, with powerful stellar winds blowing its own outer layers into space in a final, beautiful act of self-destruction. Yet when that star is gravitationally harassed by 5 stellar siblings, that mass loss is dramatically accelerated. The relentless tidal pulls from nearby companions strip material away more efficiently, like cosmic hands helping to peel the layers from an onion. This forced shedding of the star's envelope does 2 extraordinary things. First, it exposes the deeper, carbon-rich layers sooner, effectively short-circuiting the star's evolution and flooding the local environment with newly forged carbon before the star would have naturally released it. Second, and more critically, it directly affects the triple alpha process itself. By violently stripping away the outer layers, the binary interactions reduce the external pressure on the helium-burning shell. This can cause the fusion reactions to sputter and flare unpredictably, creating pulses of intense carbon production rather than a steady trickle. The stellar family, therefore, becomes a regulatory mechanism for one of the universe's most important element factories. It can force a dying star to mass-produce the stuff of life prematurely, seeding the entire system with this precious material. Any planets that might form later, or even the atmospheres of the other stars themselves, could be enriched with this gifted carbon. How many of the carbon atoms in our own bodies were forged not in a solitary, dying star, but in the gravitational storm of a complex family? Its death throes accelerated by the very siblings that had been its companions for eons. Light escaping the surface of a white dwarf must climb out of a gravitational well of immense depth. This dense stellar corpse, packing the mass of our Sun into a volume the size of Earth, creates a space-time curvature so severe it literally steals energy from the light trying to flee. According to Einstein's theory, this energy loss manifests as a subtle stretching of the light's wavelength, shifting it toward the red end of the spectrum. This is the gravitational redshift, a minuscule effect that is notoriously difficult to measure in isolation. The predicted shift is often smaller than the Doppler shifts caused by the star's own motions and atmospheric turbulence. But within the complex architecture of a sextuple system, astronomers found the perfect laboratory. They observed a white dwarf locked in a tight binary dance with another star. The predictable orbital motion of this pair provided a clean, calculable Doppler shift, a known quantity that could be precisely subtracted from the total redshift they measured. What remained was a pure, uncontaminated gravitational redshift. The other stars in the wider system acted as essential calibration points, their gravitational influence helping to pin down the white dwarf's exact mass and orbital velocity with extraordinary precision. This confirmed the predicted redshift to a degree of accuracy never before achieved, offering a beautifully clean verification of one of General Relativity's most fundamental predictions. It demonstrated that these chaotic families are not just sites of destruction, but also pristine environments for testing the universe's most delicate laws. How many other subtle cosmic effects are waiting to be measured within the intricate clockwork of a 6-star dance? A planet's allegiance to its parent star is not always a birthright. Theoretical models now reveal a far more dramatic origin story for some worlds, a celestial kidnapping enacted within the gravitational chaos of 6 suns. Picture a young, fiery protoplanet, a world still coalescing from the dust and rock of its own birth disk around one star. Its orbit is stable for a time, a predictable circle in a single stellar neighborhood. But the wider gravitational storm of the sextuple system is relentless. As the inner binary pairs whirl through their complex dance, one star swings a little too close to this fledgling world. In that moment, the planet is caught in a brutal gravitational tug of war. The pull from its original host star is suddenly matched and then overpowered by the interloper. The protoplanet is not ejected into the void. Instead, it is violently stripped from its cradle and flung onto a new, wildly erratic path that loops around the second star. In an instant, it becomes an orphan, its lineage severed, its home left behind. This captured world would bear the permanent scars of its traumatic youth. Its orbit would be profoundly tilted, perhaps even moving in a direction opposite to the other material around its new sun. Its composition could be a bizarre hybrid containing elements from two different stellar nurseries. How would such a world evolve? A patchwork planet forged from the wreckage of two separate disks. It might be a gas giant with a heart of rock from its first home, or a barren rock coated in exotic ices stolen from its adoptive family. This theoretical possibility transforms these systems into cosmic trading posts for planets, where worlds are not born into a family so much as they are bartered and stolen in a perpetual gravitational marketplace. The profound stability of a resonant sextuple system offers more than just a haven for stars. Hidden within its intricate gravitational dance are pockets of perfect equilibrium, cosmic parking spots known as Lagrange points. These are places where the combined gravitational pull from two or more stars precisely balances the centrifugal force of a small object, allowing it to remain fixed relative to the stellar dance. In a system with 6 suns, the number of these stable points multiplies into a complex web of celestial anchors. They become the most gravitationally serene real estate for light years in every direction. This theoretical calm has led to a playful yet profoundly intriguing line of speculation. If an advanced civilization ever sought a permanent foothold in a star system, a place to build a structure meant to last for millions of years, where would they choose? A solitary planet is subject to geological upheavals and orbital decay. A moon can be perturbed, but a stable Lagrange point in a resonant sextuple system is a cosmic fortress of stillness. It is a location where an immense artifact, perhaps a library, a communication hub, or a beacon, could theoretically remain parked for eons, completely unbothered by the chaotic stellar orbits around it. This idea injects a fascinating new variable into the old question of the Fermi paradox, the puzzle of why we see no evidence of other intelligent life. We often assume such civilizations would colonize simple systems like our own. But what if the ultimate cosmic engineers seek out complexity, not simplicity? Perhaps the most advanced beings prefer the ultimate stability of a 6-star gravitational ballet, building their greatest achievements in the silent, stable points we are only just beginning to calculate. While purely speculative, this thought transforms our search. We are no longer just looking for planets that might harbor life. We are learning to identify the most stable, long-term architectures the universe has to offer. Who is to say someone else has not already found them? For decades, astronomers suspected many single points of light hid complex families, but proving it was a monumental challenge. The European Space Agency's Gaia mission has utterly transformed that pursuit, turning suspicion into precise, measurable fact. This spacecraft is not merely a telescope, it is the most ambitious stellar cartographer ever built, tasked with creating a 3-dimensional, dynamic map of our galaxy. It has measured the positions, distances, and motions of over 1 billion stars with an accuracy once thought impossible. For every single one of those stars, Gaia meticulously tracks a tiny, specific wobble in its path across the sky, its proper motion. This wobble is the gravitational confession of unseen companions. A star that appears to dance a slow, jittering path rather than gliding in a straight line is being invisibly tugged by the mass of its siblings. Before Gaia, we had hints from spectroscopy and eclipses, but these were like hearing a faint, chaotic noise from a crowded room. Gaia's data gives us a live video feed of the entire dance floor. It measures the minuscule side-to-side sway of a star so precisely that it can reveal the gravitational pull of a planet, a brown dwarf, or another star. When applied to known sextuple candidates, this data has been the final, irrefutable proof. The suspected 6-star systems, once models based on complex calculations, have now been confirmed. Their intricate gravitational architectures, with stars subtly pulling each other in a dozen different directions, are laid bare in the data as clear, quantifiable paths. But the mission's greater impact lies in discovery. By sifting through the motions of a billion suns, astronomers have found entirely new sextuple systems that were completely invisible to all other methods. These are families where no eclipses occur, no spectral lines are scrambled, and no pulsars tick. Their only giveaway was the gentle, rhythmic sway of their primary star against the backdrop of the cosmos, a wobble so small only Gaia could see it. This mission has effectively handed us a census of stellar multiplicity, revealing that these complex families are not the rare cosmic oddities we once believed, but a fundamental and surprisingly common way for stars to exist. The ultimate destiny of these stellar families is written in their immense collective mass. A truly massive sextuple system is a ticking clock, its hands forged from the relentless pull of gravity. Over billions of years, the violent dance we have witnessed will reach its final, inevitable crescendo. Stellar mergers will create ever larger suns. Those bloated giants will then die in furious supernova explosions, each collapse leaving behind a dense stellar corpse, a neutron star or a stellar mass black hole. These dark remnants will continue their ghostly waltz within the system, a dance of the dead. But gravity is not finished. In the most crowded and massive of these families, these black holes and neutron stars will themselves be drawn together. They will spiral inward, their orbits decaying through the emission of gravitational waves until they too collide and merge. One by one, the 6 stars will vanish, consumed by the growing darkness they have collectively birthed. The final product of this cosmic consolidation could be an intermediate mass black hole, an object possessing the mass of thousands of suns all crushed into a single point of infinite density. This is not the end of the story, but a profound new beginning. Astronomers have long puzzled over how the supermassive black holes at the hearts of galaxies, behemoths weighing millions or even billions of solar masses, could have grown so large so quickly after the Big Bang. An intermediate mass black hole provides the missing link. It is the perfect seed. Once formed in a dense star cluster, this hefty seed would have a tremendous gravitational advantage. It would rapidly sink to the center of its host cluster, greedily devouring any gas, dust, or stars that stray too close, ballooning in size over the eons into the galactic monsters we observe today. The chaotic, brilliant life of a family of 6 suns may therefore be the crucial, hidden nursery for the most dominant gravitational forces in the universe. The same gravity that bound them together in a complex ballet ultimately devours them, transforming a symphony of light into a silent, gravitational titan that will one day rule the center of an entire galaxy. These 50 discoveries reveal a cosmos far stranger and more diverse than we ever imagined. We have encountered stellar vampires locked in parasitic dances, cosmic factories forging rogue planets and interstellar comets, and stellar zombies endlessly cheating death. We have seen gravity warp into a lens space-time hum with silent waves, and the very chemistry of stars rewritten by their chaotic families. These are not mere astronomical curiosities. They are fundamental laboratories testing everything from Einstein's theory of gravity to the very rules of stellar life and death. They challenge our definitions of what a star can be, what a planet can endure, and what kind of order can emerge from the most profound chaos. The next time you gaze up at a seemingly solitary point of light, remember the truth. That star could be a crowded metropolis, a family of 6 suns engaged in a gravitational ballet of breathtaking complexity. Their hidden stories are written in the wobble of starlight, the timing of eclipses, and the silent pull of dark remnants. Our journey is just beginning. Who knows what other celestial wonders are hiding in plain sight, waiting for the right moment to reveal their secrets. Keep looking up and never stop wondering what lies beyond the next star. If you want to continue exploring the deepest mysteries of the cosmos, subscribe for more journeys to the edge of our